Hi, welcome back again to the second part of geometric distribution lesson. So in the first part of the lesson, we looked at if x follows a geometric distribution with probability of success p, then the PMF is given by 1 minus p to the power of x minus 1 times p for x equals 1, 2, 3, and so on. We also found out that the CDF is equal to 1 minus p to the power of x, and the survivor function, which is the probability that x is greater than little x, is given by 1 minus p to the power of x. In this lesson, we're going to derive the MGF, the expectation, the variance, and finally show that a geometric distribution or a geometric random variable has a memoryless property. So let's find the MGF of this random variable x. The MGF, mx of t, the moment generating function, is the expectation of e to the power of t times x. Now the support of this random variable is the values 1, 2, 3, 4, and so on. So this is the same as the summation x starting from 1 to infinity of e to the power of t times x times the PMF. And that is equal to the sum x starting from 1 to infinity of e to the power of t times x, and the PMF is 1 minus p to the power of x minus 1 times p. What I'm going to do now is I'm actually going to simplify these two expressions. E to the power of tx can be written as e to the power of t to the power of x. Also, 1 minus p to the power of x minus 1 can be written as 1 minus p to the power of x divided by 1 minus p. Okay? Utilizing this expressions that I have, I can write this moment generating function as the sum x from 1 to infinity of e to the power of t, the whole thing to the power of x, times 1 minus p to the power of x divided by 1 minus p times p. But I can take p divided by 1 minus p outside of the summation. So I have p divided by 1 minus p times the sum x starting from 1 to infinity of e to the power of t multiplied by 1 minus p to the power of x. Okay, I can combine these two because they have the same power, which is x. Now if e to the power of t times 1 minus p is less than 1, then I would have a converging geometric series. So we know if the common ratio of a geometric series is between 0 and 1, then the sum converges. In fact, what I'm going to do here is, you can see here x begins from 1, but our geometric series formula is k from 0 to infinity of r to the power of k is 1 divided by 1 minus r, if r is between 0 and 1. I need to have an index that starts from 0, but this one starts from 1. But that is easy to fix. So I can do p times 1 minus p times, if I add to the summation, this is e to the t 1 minus p to the power of x. If I add to that summation e to the power of t times 1 minus p to the power of 0, and subtract e to the t times 1 minus p again to the power of 0, I haven't changed that sum because I've added a number and subtracted a number. And fortunately enough, that number is simply 1. So I've added 1 and subtracted 1. So if I include these two terms. This 1 to the power of 0. With the rest, I would have p divided by 1 minus p times the sum x now starts from 0 to infinity of e to the power of t times 1 minus p, the whole thing to the power of x, minus 1. Now this is a geometric series, so it simplifies to 1 divided by 1 minus the common ratio, which is e to the t times 1 minus p. Then I have minus 1. Therefore, I can simplify this further as the denominator becomes 1 minus e to the power of t times 1 minus p, and I have 1 minus e to the power of t times 1 minus p, and that is equal to p divided by 1 minus p times 1 minus 1 is 0. I have negative 1 times the negative of that expression, that's positive. So that is e to the power of t times 1 minus p divided by 1 minus e to the power of t times 1 minus p. But 1 minus p here cancels out 1 minus p here. Therefore, the MGF has the following expression. The MGF of a geometric random variable x has the expression p times e to the power of t divided by 1 minus e to the power of t times 1 minus p. If, we don't have to forget that condition, if e to the power of t times 1 minus p is less than 1. E to the power of t times 1 minus p is less than 1. Or this can be written as t less than the negative natural log of 1 minus p. We have the MGF. Now let's go ahead and find the expected value of the random variable x. Okay, the expected value is, x is discrete, so the expected value is the sum over all the support of x, which is x starting from 1 to infinity, of x times the PMF. Okay, that's one way to find the expectation of a random variable. The other way to find the expectation would be to use the MGF technique. That is, the expected value of x would be the derivative of the MGF with respect to t evaluated at t equals 0. I'm gonna let you decide which one is easy. So I'm gonna solve first using the definition of MGF, using the definition of expectation, and also using the MGF technique. And you decide what's easier. Let's do this first. So this is equal to the sum x from 1 to infinity of x times the PMF, which is 1 minus p to the power of x minus 1 times p. But here, p does not depend on x, which is the index of the summation here, so I can take it outside. So I have p times the sum x from 1 to infinity of x times 1 minus p to the power of x minus 1. If you look at this expression carefully, that looks very similar to the antiderivative of 1 minus p to the power of x times negative 1. What I mean by that is, if you actually take the derivative with respect to p of that expression, you would get x times 1 minus p to the power of x minus 1. So let's take the derivative. So this is minus 1 times the derivative of 1 minus p to the power of x is x times 1 minus p to the power of x minus 1 times the derivative of the inside function 1 minus p with respect to p. So the derivative of 1 minus p with respect to p is negative 1. Okay, so I have negative 1, that's going to be positive. So I have x times 1 minus p to the power of x minus 1. So instead of x times 1 minus p to the power of x minus 1, I could write the derivative with respect to p of minus 1 times 1 minus p to the power of x. So that the expectation would be equal to p times the sum x starting from 1 to infinity of the derivative with respect to p of negative 1 times 1 minus p to the power of x. Negative 1 is a constant with respect to p, so I can take it outside of the derivative. Okay? In fact, I can actually take it outside of the summation because it does not depend on x. So take that outside of the summation. So you have negative p. So the expectation would be minus p times the sum x from 1 to infinity of the derivative with respect to p of 1 minus p to the power of x. You want to next interchange the derivative and the summation so that you have minus p times the derivative with respect to p of the sum x equals 1 to infinity of 1 minus p to the power of x. You almost have a geometric series. Actually, you have a geometric series. If you add 1 minus p to the power of 0 and subtract 1 minus p to the power of 0 from this summation, you get the following. This would be equal to negative p times the derivative with respect to p of the sum x starting from 0 to infinity of 1 minus p to the power of x minus 1 minus p to the power of 0, which is 1. Okay, so the reason why I did this is to have the index of the summation start from 0 instead of 1. So that I have this as d by dp of 1 over 1 minus p. A geometric series sums to 1 divided by 1 minus the common ratio. In this case, the common ratio is 1 minus p, minus 1. So this equals minus p times the derivative with respect to p of 1 over the denominator simplifies to p minus 1. And take the derivative of 1 minus p minus 1 with respect to p, you get the following. Minus p times minus 1 divided by p squared. If you simplify this, you get 1 over p as the expectation of the random variable x. Okay? You could also find the expectation by using the MGF technique. To do that, first I need to find the derivative with respect to t of the MGF. We have the MGF, which is right here, p times e to the t divided by 1 minus e to the t times 1 minus p. So we need to take the derivative with respect to t of p times e to the t divided by 1 minus e to the t times 1 minus p. I can use the quotient rule, which tells me to take the derivative of this ratio, I need to multiply the denominator, 1 minus e to the t times 1 minus p, by the derivative of the numerator, d by dt, of p times e to the t, minus the numerator, p times e to the t, multiplied by the derivative of the denominator, 1 minus e to the t times 1 minus p, the whole thing divided by the square of 1 minus e to the t times 1 minus p square. Okay, now let's go ahead and take those derivatives, that one and that one. So we have 1 minus e to the t times 1 minus p multiplied by the derivative of p times e to the t with respect to t is simply p times e to the power of t minus p times e to the t multiplied by the derivative with respect to t of that expression is minus e to the t times 1 minus p. Okay, now divide everything by 1 minus e to the t times 1 minus p square. Let's simplify this. Multiply p times e to the t by 1, you get p times e to the t. Multiply this by that expression, you get minus times p times e to the t times e to the t times 1 minus p. Minus, have minus, minus, that would be plus p times e to the t times e to the t times 1 minus p, divided by 1 minus e to the t times 1 minus p squared. Now you can see this expression cancels out with that one. They're exactly the same. One is positive, one is negative. Therefore, the derivative with respect to t of the MGF mx of t is given by p times e to the t divided by 1 minus e to the t times 1 minus p square. To find the expectation, therefore, what I have to do is plug in 0 for t. So when you plug in 0 for t in this derivative, you get p times e to the power of 0, which is 1, divided by 1 minus e to the power of 0 is 1. So 1 times 1 minus p square. So 1 minus p is equal to p. Therefore, I have p divided by p squared, which is equal to 1 over p. So I have the same expectation that I found using this way is exactly the same as this one. Alright, now let's find the variance. The variance of this random variable x is equal to the variance of x is the second moment, the expected value of x squared, minus the first moment, which is the expected value of x the whole squared. And we know the first moment. We have just found it, which is 1 over p. So 1 over p squared is the square of the first moment. So we know that we only need to find the expected value of x squared so that we are able to find the variance of x. But the expected value of x squared is equal to the second derivative with respect to t of the MGF mx of t evaluated at t equals 0. Therefore, what I need to do now is find the second derivative with respect to t of the MGF. So that second derivative is equal to mx of t is equal to the first derivative of the derivative with respect to t of the MGF. But we know the derivative with respect to t of the MGF. This is right here. So I can write this as the derivative with respect to t of p times e to the t divided by 1 minus e to the t times 1 minus p square. Okay. Now, this is equal to the derivative with respect to t of p times e to the t divided by 1 minus e to the t times 1 minus p times 1 over 1 minus e to the t times 1 minus p. What I simply did is, instead of having the square here, I have to the power of 1, but multiply by 1 over the denominator. So those two expressions are the same. But this gives me something really nice in terms of computation, because this expression here is actually simply the MGF, mx of t. So what I am able to do now is write the second derivative with respect to t as the derivative of the MGF divided by that expression, 1 minus e to the t times 1 minus p. I can now go ahead and use the quotient rule, which gives me 1 minus e to the t times 1 minus p times the derivative with respect to t of the MGF minus the MGF, mx of t, times the derivative with respect to t of 1 minus e to the t times 1 minus p divided by the square of 1 minus e to the t times 1 minus p. Okay, almost there. So this is equal to 1 minus e to the t times 1 minus p times the derivative with respect to t of mx of t minus mx of t times the derivative with respect to t of 1 minus e to the t times 1 minus p, which gives me minus e to the t times 1 minus p divided by 1 minus e to the t times 1 minus p square. Now, since I have a minus here, I can get rid of that minus, move it out, which makes this minus a plus. Okay, so to find the second moment, what I need to do is plug in 0 for t and the expression that I have. So the expected value of x squared is this expression evaluated at t equals 0. So when I plug in t equals 0, e to the power of 0 is always going to be 1. So I have 1 minus e to the power of 0, which is 1, times 1 minus p, okay, times the derivative of the MGF evaluated at t equals 0 is the expected value, right? So the expected value of x, which we have found to be 1 over p. So that is, instead of that, I plug in 1 over p. Plus, what is the MGF evaluated at 0? By definition, MGF, mx of t, is the expected value of e to the power of t times the random variable x. But if t is equal to 0, I have e to the power of 0, which is 1. Expectation of 1 is always 1. So the MGF evaluated at 0 is always 1. 1 times, plug in 0 for that, you get 1 times 1 minus p divided by 1 minus e to the power of 0 is 1 times 1 minus p squared. So this is equal to 1 minus p is p. Then I have 1 over p here. 1 over p minus, plus 1 times 1 minus p is 1 minus p divided by, now this is equal to 1 minus p is p, and it has to be squared. Therefore, this is 1 plus 1 minus p divided by p squared, which is 2 minus p divided by p squared. That's the second moment. But the variance of the random variable x is the second moment minus the first moment, which is 1 over p squared. So I have 2 minus p divided by p squared minus 1 over p squared. Take p squared as the common denominator, then you have 2 minus p minus 1. Okay, so the variance is equal to 1 minus p divided by p squared. If we have a geometric random variable x with probability of success p, geometric with probability of success p, then the expected value of x is 1 over p, and the variance of x is equal to 1 minus p divided by p squared.